Okay, the topic of the lecture are oscillatory phenomena, and in particularly oscillations that occur in nonlinear systems and limit cycle oscillations. So what is a limit cycle? I will explain it soon, but first let me show you some example of oscillations that we have already seen. Namely, the first example is the simple linear oscillator that we see here. This is its differential equation. We know that we can transform it in a two-component system by introducing a new variable y, and in the following form. Okay, so this is a simple system that we can solve exactly, and if we plot the phase space here, we have the xy plane. These are closed orbits, so oscillations are described here by closed orbits. So the system repeats this circular cycle. So there is a fixed point here in 0, 0. The Jacobian matrix, if you calculate it, it's very simple. It's already given here. You don't have to do linearization. It's already a linear system. So if you take this matrix, you see that its trace is 0 and the determinant is positive. This is a center. So a simple oscillation, and this is a linear system. Okay. We have seen also very similar oscillations in a nonlinear system, namely here it's a Lotka-Volterra system. These are the differential equations describing this system. So x dot is x multiplying alpha minus beta y dot is minus y gamma minus delta x. Okay, this is a nonlinear system because we have a coupling term x times y times x here. All right, and describes a system of preys and predators. Okay, x is the prey and y is the predator. The phase space has similar features as that of a linear harmonic oscillator. It's still nonlinear, but there are these closed orbits around the fixed point. So there are oscillations in the population of preys and predators. In a very similar fashion, there is around the fixed point, there is an infinite orbit of an infinite amount of oscillation, all right, of oscillatory orbits. Okay, this is the center. Okay, very similar to that of a linear harmonic oscillator. Okay, so what we discussed today is a different situation, and it is shown here on the top right side of the whiteboard, is that of a stable limit cycle. So the stable limit cycle is instead characterized as a single isolated oscillatory solution, which is described here by this blue closed curve. So the system now the system runs around many times and performs oscillations of this type, and we are particularly interested in stable limit cycle, and those are cycles in which the phase portrait is such that if I start from inside this cycle, then the flow tends to converge towards it, and if I start from outside, the flow is attracted towards the limit cycle. So what is the nice feature of these oscillations compared to the harmonic oscillator, for instance? So let's start from the harmonic oscillator. You perturb it a little bit. So say that you are running in an orbit of the harmonic oscillator or the Lotka-Volterra system. So it's one of these closed curves, all right? And the system is deterministic, so it will run around this forever. Suppose now we have a perturbation on the system. The perturbation kicks my x or my y to another orbit, and then the perturbation is released, okay, and then you will continue with the other orbit. So you see that the system, it's very sensitive here, the harmonic oscillator, or this type of oscillations of when you have an infinite set of orbits, the system is very sensitive to any perturbation that kicks you out of a given orbit and brings you to another orbit. Even if when the perturbation is released, you're still in a different orbit. Okay, It's like a harmonic oscillator, you give a bit more energy, you jump to another state, and so on, another orbit. All right, this does not happen when you have a stable limit cycle, because if a perturbation brings you out of the limit cycle, when the perturbation is removed, then you're back. All right, and the same happens if you go inside the limit cycle by the action of a small perturbation, then you are drawn back towards it. So, okay, this is a nice feature of this stable limit cycle type of oscillations that are much more robust compared to the one that we see in harmonic oscillator and in the Lotka-Volterra model. All right, so this is the discussion of our limit cycle. As an example, I would like to start with what is called the van der Pol oscillator, which is a system, an oscillator, described by the following differential equation. Okay, so we have x dot dot is equal to this nonlinear term, is multiplying x dot minus x. Okay, so this term in red can be seen as a kind of friction. So if this were just a coefficient minus gamma, say, this would be the damped harmonic oscillator equation, the linear equation describing a damped harmonic oscillator. But it's not just a constant friction, it's a peculiar type of friction, and in particular this friction changes sign. For x larger than 1, this looks like a bit the ordinary friction, a negative coefficient in front of here. But for x smaller than 1, it's a positive term, and this is a kind of an unphysical friction. That's why I put between quotes the friction is something that pumps energy into the system. You know that the friction is a dissipative force. It removes energy from the system, the ordinary friction. So that's what happens also here when x is larger than 1. But when x is smaller than 1, that you have the opposite effect. You have an increase in energy. You're pumping more energy into your system. Okay. So again, we do the analysis and we transform it into a system of two equations, okay, with first order derivatives, and this is given by this. There is a fixed point on this van der Pol oscillator, and I can do the analysis of this fixed point, and this is shown here. The linearization around 0, 0, okay, gives me this this linear equation where the matrix A is the Jacobian, and if I do the analysis, trace of A and that of A, trace of A is equal to mu, and the determinant of A is 1, therefore it's positive, and for mu positive, this is an unstable node. Okay, this is an unstable node, and if we plot the phase portrait, we see that this van der Pol oscillator has a limit cycle. This is shown here in blue. Okay, the fixed point in 0, 0, and this is a stable limit cycle. The fixed point is actually unstable, so the flow goes out of this fixed point until it reaches the limit cycle, whereas at outside the limit cycle, the flow tends to be attracted towards the limit cycle. Okay, so this is a stable limit cycle, and we can give a kind of intuitive picture of this. So if I start from outside the limit cycle in this region, this is a region where x is larger than 1, so the system is like a damped harmonic oscillator. The damped harmonic oscillator would like to bring you this point towards the origin. Okay, that's the damped harmonic oscillator, and that's a stable point. But this is not what happens here. It doesn't happen because when you are close to the origin, actually the friction changes sign. So there is energy is pumped into the system. This point is unstable, and that's why you have a limit cycle. It's a kind of balancing these two type of frictions, the positive, the ordinary type of friction at large x with this kind of inverted friction which pumps energy into the system at small x, and this is what gives rise to the limit cycle. And what we find here particularly is that, yeah, inside the limit cycle there is a fixed point, and this fixed point is unstable, and this is a typical situation which we will encounter in many other examples. Okay, this is yet another example and comes from the book of Strogatz. This is an example of a limit cycle that of a system that I write like this in polar coordinates. So I have two coupled differential equation, one for r and one for theta. R the radius and theta the angle. Okay, so these are polar coordinates. So for r, there is this following differential equation: mu times r minus r cubed, and for theta dot is equal omega plus b r square. Mu, b, and omega are some parameters. Okay, so it's a two-component system, but actually what I can do here, I solve first the differential equation for r, then I plug in the solution here and I solve for r. So the differential equation for r is independent. Okay, so that I can look, this is a one-component system, therefore I know how to solve it. Okay, so we have two different cases here. So let's say that mu is positive, then I plot this function, the function that I have here on the right hand side. So this is a cubic, right? For small for small r, it's growing linearly, mu times r, but then it's a cubic and with a minus sign that it goes down like this. So for mu is positive, there is one intersection here. There is a fixed point at that intersection here. There is also one here, but we are only looking now for this one. This takes place, this corresponds to a value of r, let's call it r star, equal to the square root of mu. Okay, this is for mu is positive. For mu is negative, then you see that this is the behavior of the function. When mu is negative, so the function for all r is negative except for r equal to 0. Okay, so this is what we find. So there would be a fixed point. So this is a circle of radius square root of mu. Okay, this is and theta dot is equal to that. It's some angular variable that keeps rotating. Okay, so we can analyze this system also in polar coordinates. And so what we do, we change variables, and instead of r and theta, we work with x and y. Okay, and this is the differential equation transformed. Okay, there are dots here that are higher order terms. Here I want to specifically analyze what happens for x and y small. So I'm looking at around the fixed point where in the origin. Okay, so this is the fixed point. So I can read the Jacobian matrix is mu on the diagonal and omega minus omega. The eigenvalues are immediate, one can calculate them immediately. This is mu plus or minus I omega. Okay, so you see what happens when so the situation is therefore as follows. When in the plane x, y, so in the phase plane, if I look at these Cartesian coordinates, okay, when mu is larger than 0, we have established that there is a fixed point. So this is a circle of radius square root of mu, and this is the limit cycle. Okay, so that's how the system behaves. For mu is positive, the eigenvalues are these. For mu is positive, this tells me that our fixed point is an unstable spiral, spiraling out. Okay, when r is sufficiently larger than 1, so we see that r dot is negative, therefore there is an attractive limit cycle here. So from outside, the flow tends to spiral, to go in towards the limit cycle, and from inside, from the origin, we have an unstable fixed point. Okay, when mu is negative, we are in these situations. Our eigenvalues get a negative real part, and this describes a stable spiral. Sorry, so the flow starting from here flows and rotates and go into a stable spiral. Okay. into a stable spiral state. Okay, so you see that there is a critical difference between the two cases, and this is what we in a linear system is called a bifurcation. Actually, this type of bifurcation is called a Hopf bifurcation. The value where this separating these two cases is mu equal to 0. This is called a Hopf bifurcation point, and it plays a central role in this theory, in this theory of limit cycle. So okay, so exactly, so when going from negative mu, we hit at mu equal to 0 the Hopf bifurcation point, and we go to mu positive, we have the emergence of a limit cycle. So if mu is positive and very small, the radius of this limit cycle is much smaller. It's very small, okay, and it starts growing and grows with the square root of mu as mu becomes larger and larger, so this limit cycle increases, okay. So this Hopf bifurcation theorem says that typically around the Hopf bifurcation point, I will have a limit cycle, okay. And okay, so we discuss in the next this Hopf bifurcation theorem.